Hello students, hope you are doing well. So today's topic is group 15 elements. So let us see. That is, the elements are nitrogen, phosphorus, arsenic, antimony and bismuth. Okay. Now, general electronic configuration of the outermost orbital will be our ns2 np3. Then what are the atomic properties? Atomic properties are atomic radii increases down the group, I decreases down the group, and En decreases down the group. Those are physical properties. What is the physical properties? There are many physical properties, but two of them are most important. That is our boiling point and melting point. So boiling point increases down the group, and melting point increases up to arsenic. Okay, but decreases up to Bi. Then our chemical properties. Chemical properties first is our oxidation state. Oxidation state that you can see in this group, there are three oxidation states, that is -3, +3 and +5. Now reactivity towards hydrogen, that is of EH3 type. That means where E equal to NPAS, SB and Bi. That means NH3, PH3, okay, ASH3 like this. Now let us see the trends of the hydrides. Okay, so bond angle is NH3 greater than PH3, greater than ASH3, greater than SBH3, greater than our BiH3. That means down the group bond angle decreases, right? Now why this bond angle decreases down the group? Because of the electronegativity on the central atom. That electronegativity on the central atom decreases down the group. That's why bond angle also decreases down the group. Okay. Then these are thermal stability. Thermal stability also decreases down the group, and basicity also decreases down the group. But in case of reducing character, as we can see, it increases down the group. That is why BiH3 greater than SBH3 greater than ASH3 greater than PH3 greater than our NH3. Then our boiling point. Now, boiling point is also increases down the group, but there is a variation. That is BiH3 greater than SBH3, but NH3 comes in between them, and then our ASH3 and pH3. Okay. Melting point also increases down the group, but NH3 has the highest melting point than the rest of the four. All the rest of the four are increases down the group melting point, but only NH3 is the exception. Okay. Now reactivity towards oxygen, that is E2O3 or E2O5 type. Okay. Now in E2O3, as you can see, the acidic oxides are formed by our nitrogen and phosphorus. Amphoteric oxides are formed by AS and SB, and basic oxide is formed by our Bi. Next is oxides of nitrogen, that is N2O, charge on N2. Now I'm writing this charge here because they are like this: +1, +2, +3, +4, and it is +5. So as you can see, if you just remember their order like this, that is N2O, NO, N2O3, NO2, N2, 5. So you don't have to remember the charge. You will just 1, 2, 3, 4. It will be in order. Okay. So this is their structure here also drawn. Okay, as you can see. Now, in case of N2O5, as you can see here, there is a bridging oxygen. So question comes, in which of the oxides of nitrogen bridging oxygen is present? So that will be our N2O5. Next is acidic order. Now, acidic order is acidic character increases if we come into O2 into O5. So let us write the acidic order, that is N2O5 greater than NO2 greater than N2O3 greater than NO greater than N2. Next is reactivity towards halogen. That is our EX3 or EX5. That means it can be NCl3 or PCl3, PCl5, the nitrogen. We have shown here preparation reactions of nitrogen, that is NH4Cl plus NaNO2, that is N2 plus 2H2O plus our NaCl. It is our lab preparation. Okay. Now the rest of the three are heating reactions. They are not lab reactions, but we can also get N2 from there. That is NH4 whole twice Cr2O7. If we heat it, it gives us N2 plus 4H2 plus Cr2O3. And BaN3 whole twice, if we heat it, it gives us Ba plus 3N2. And if 2NaN3, if we heat it, then it gives us 2Na plus 3N2. Next is our ammonia. Ammonia is preparation reaction is shown here. That is called Hebert's process. Okay. Now, as you can see, it is 1 mole of N2 and 3 mole of H2 is added and reacted to form 2NH3. Now, in this reaction, pressure will be 200 into 10 to the power 5 Pascal or 200 atm, and temperature will be 700 Kelvin. And the catalyst will be our iron oxide with small amount of K2O and Al2O3. Now, properties of ammonia, that is first is our structure. So, as we can see, the structure is our pyramidal. Okay, because one lone pair is present here. Hybridization will be sp3 and bond angle will be our 107.5 degree. Next is our reactions of some reactions of ammonia, that is Cu plus 2 plus 4NH3. It forms CuNH3 whole 4 plus 2. Now this compound has a special property, that is in aqueous solution. Now this CuNH3 whole 4 has a special property, that is this Cu plus 2 in aqueous solution, it is blue color. Okay, but when it is reacted with ammonia, it forms a square planar structure, that is our CuNH3 whole 4 plus 2, and its color will be deep blue. Okay. Now here another reaction is shown, that is Ag plus plus Cl minus forms AgCl, which is white. But when it's reacted with 2NH3, that it forms AgNH3 whole twice Cl, and it has no color. That means the solution becomes colorless. Okay, so on the basis of color, it is very important. Now next are some reactions of ammonia shown accumulatively. That is, if NH3 is reacted with Na, it forms bronze color sodamide. Okay, sodamide. And if it is reacted with B2H6 red heat, it forms boron nitride, or we know it inorganic graphite. Okay, so we have seen it in the group 13 elements. Next is, if it reacted with O2, if it is reacted with limited O2, then it forms N2 plus H2. But if it is reacted with excess O2, that it forms NO plus H2. Also, in case of Cl, if it is reacted with limited Cl2, it forms NH4Cl plus N2. If it is reacted with excess Cl2, it forms NCl3 plus HCl. Next is our B2H6. Okay, if it is reacted with 1:2 ratio, then it forms B3N3H6 or inorganic benzene. Next is NH3. If reacted with NaOCl, it forms N2 plus NaCl plus H2O. So it is a NaCl forming reaction here. Next is our NH3. If reacted with this compound, that is K2HgI4, this is called Nessler's reagent. Okay, it forms NH2 HgO, HgI, and its color is brown. Okay, so why this is important? This compound, that is, it forms iodide of millions base. Okay, which is also test for what? NH3. Okay, next is our nitric acid. Nitric acid's formula is HNO3. In structure is like this. This angle will be 102 degree and this angle will be 130 degree. Now let us see some reactions. That is, first is our preparation reaction in the lab. So lab reaction is NaNO3 plus H2SO4. It gives us NaHSO4 plus HNO3. So please remember this equation, because this reaction is often asked in NEET. Okay, they will ask you the byproducts also, so please remember it. Then if we want to produce NH3 in large amount, then comes the process called Oswald's process, where if we give 4 amount of NH3 and 5 amount of O2, PTRH Gauge catalyst, 500 Kelvin temperature, 9 bar pressure, and it forms 4NO plus 6H2. Then from 4NO we take 2NO plus O2 and it forms a reversible reaction, that is 2NO2. Now 3 amounts of NO2 is dissolved in our water, then it forms 2HNO3 plus NO gas. Now this NO gas go vaporized and only the HNO3 remains. Next are the reactions of HNO3. So first is 3Cu plus 8HNO3 diluted. That means copper is reacted with diluted HNO3. It forms 3CuNO3 whole twice plus 2NO plus 4H2. Then the same metal Cu is reacted with concentrated HNO3. Then it forms CuNO3 whole twice, but here 2NO2 plus 2H2. Then Zn is also reacted with diluted HNO3 and it forms ZnNO3 whole twice plus 5H2O plus N2. Then again Zn is reacted with concentrated HNO3. Now it forms ZnNO3 whole twice plus 2H2O plus 2NO2. Now you guys are thinking that why these 4 reactions are written and called special? Because the concentrated case, it is always forming NO2. Can you see it as a byproduct? But when we are reacting copper with diluted HNO3, it forms NO. Okay, but when we react Zn or zinc with diluted HNO3, it forms N2O. That means the byproducts are varying in case of diluted acid. Okay, so in case of copper, it forming NO, and in case of Zn, it forms N2O. Next is our HNO3's oxidizing property is shown here. That is, if it is reacted with I2, it gives us the respective acid, that is HiO3. If it is reacted with carbon, then it forms CO2. If it is reacted with S8 or sulfur, then it gives us H2SO4. Okay, and in case of our phosphorus, it gives us H3PO4 or phosphoric acid. Now as you can see, the byproducts are same, that is NO2, NO2, NO2 and H2. Next is our brown ring test for nitrates. So here you can see that NO3 minus and 3Fe2 plus plus 4H plus forms NO plus 3Fe3 plus plus 2H2. Here Fe-H2O whole 6 plus 2 plus NO. NO and goes into this coordinate ring. Then Fe-H2O5 NO plus 2 and H2, and this whole compound forms a brown ring. So the test is done by adding dilute FeSO4 to an aqueous solution of NO3, then adding the H2SO4 along the sides. When it is added, then what happens? At the junction of this H2SO4 and this NO3 and FeSO4 solution, it forms the brown ring. That's how we identify it. Okay. Next is our phosphorus. Now phosphorus can be of 3 types. That is red phosphorus, white phosphorus, and black phosphorus. In between among these 3, only the red and white phosphorus is important. Now let us see, that is it is red phosphorus. So red phosphorus is like this, a discrete tetrahedral molecule, okay, and it is very reactive. Now why it is reactive, that we can see if we draw imaginary line here, that it forms 60-degree bond here, so that's why it is very reactive, okay. Then it is soluble in CS2 but insoluble in water, and it glows in dark. We call this property chemiluminescence, okay. Next is our phosphine production. So it is a very important reaction. Try to remember it. That is P4 plus 3NaOH plus 3H2O. Now this H2 is boiled. Okay. Now sometime there is a question, that is boiling water and our red phosphorus reaction is given in presence of NaOH. So you have to see in the options that if these two of these products is present or not. Okay. So here pH3 is formed, that is also called phosphine, and this is Na2H2PO2. Okay. Next is our white phosphorus. Now in this white phosphorus, what we can see, that it is forming a polymer type of chain, okay. So it is insoluble in water and CS2 both, okay. Next is our black phosphorus. Now there is nothing to be read in black phosphorus, just remember that there is two of the forms, that is alpha phosphorus and black phosphorus, okay. Then comes our phosphine, that is pH3. Now this is the preparation reaction, that is Ca3P2 plus 6H2O gives us 3CaOH whole twice plus 2pH3. Now properties, it is weakly basic, okay, weakly basic in nature. Huh? So it forms pH3 plus HI pH4i, used in home signals. In our SOS signal, we can call it PCl3. Now PCl3, the structure is like this, okay. That is sp3 hybridized and pyramidal structure. Preparation is P4 plus Cl2. Here P4 is white phosphorus, it gives us 4PCl3. Now properties, as we know in the organic chemistry, to form any haloalkanes from alcohol, or we can say from acid or aldehyde, we use PCl3. That is C2H5OH plus PCl3 gives us C2H5Cl. CH3COOH plus PCl3 gives us CH3COCl. CH3CHO plus PCl3 gives us CH3CHCl. Now the next part is our PCl5. Now PCl5 has a characteristic structure and form, and we have shown it in our hybridization video. So if you haven't watched the video, please go and watch. We have put the link in the description, so please go and watch it. So next is our preparation. Preparation is P4 plus 10Cl2 gives us 4PCl5. Now properties, PCl5 plus H2O gives us POCl3 plus 2HCl, and POCl3 then hydrolyzed and gives us H3PO4 plus 3HCl. Next is PCl5 plus CH3COOH gives us CH3COCl. Next is PCl5 plus CH3OH gives us CH3Cl. And PCl5 is heated, it gets broken in PCl3 and Cl2. Then if we react it with a metal, that is Ag, it gives us the metal chloride, that is AgCl. Okay. Two of the most important structures. Okay. So as you can see here, that this is a structure for P4O6. Now in NEET questions, they ask you how many lone pairs are there on phosphorus in total. So as you can see, 1, 2, 3, 4 lone pair is present. So 4 lone pairs in total. They just ask you this question. Okay. So in case of P4O10, as you can see, the lone pairs are bonded with O atom. So here is no lone pair is present. So they ask you how many lone pairs are present in P4O6 and P4O10. In P4O6, it will be 4 on the phosphorus atom, and in case of P4O10, there is no lone pair is present on above the phosphorus. So oxyacids of phosphorus. So many of us are having problem in remembering their names. So just remember this order. Okay, it is hypo, ortho, pyro. Not only in this oxyacid, in every oxyacids, it will form, or what I can say, it will always follow this hypo, ortho, pyro order. And the first is our phosphorus acid, that is hypophosphorus acid, orthophosphorus acid, then pyrophosphorus acid. If the up to we go to pyro, then again it will form hypophosphoric acid, orthophosphoric acid, pyrophosphoric acid. That's how we name it. Then let us see the structures. I have shown you the important structures only. That is H3PO2. As we can see, that is a double bond is present on the upper side of P, and here is OH, and two H are present here. Okay, and the oxidation state will be our +1 on P. Then H3PO3. H3PO3, we can see that one hydrogen is less here and is replaced by our OH, and its oxidation state will be +3. Then H4P2O5, its oxidation state will also be +3. Its structure is not that important. So fourth acid will be our H4P2O6. It is also +4. And for H3PO4, we can see its oxidation state will be +5. And here we can see every hydrogen is replaced with OH, and it now we are seeing H4P2O7. So its oxidation state will also be +5. And here is a characteristic bridging O is present. Okay, so if they ask you in which of the following acids bridging oxygen present, that will be H4P2O7. Now for the naming, if we name it, so I have told you the order hypo, ortho, pyro. So it will be hypophosphorus acid. Then again it will be orthophosphorus acid, and it will be pyrophosphorus acid. H4P2O6 will be called hypo hypophosphoric acid. It will be orthophosphoric acid, and the last one will be our pyrophosphoric acid. Okay, so this is it for our group 15 elements.